Hello, my name is Brenna Curtis, and this is my presentation on the grain size analysis of Oligocene loess deposits. The analysis of loess deposits is really important as people try to reconstruct the paleoclimate because just the mean grain size and the distribution of grain sizes can indicate different transport mechanisms. And loess deposits of the late Eocene and Oligocene ages have been identified in North America, but there haven't been too many detailed studies. This project aims to kind of examine the Oligocene loess deposits in northeastern Colorado near Pawnee Buttes a little bit closer. So originally, samples were collected as two separate sites or labeled PB and PBE. However, it was noted that they were in the same stratigraphic column and actually they overlapped. So for the purposes of this study, they were treated as one site. Samples were prepared by being ground in a mortar and pestle and sieved through a 1 millimeter sieve. Then about 0.5 grams of each sample was measured out and treated first with hydrogen peroxide to remove organic matter, and then hydrochloric acid to remove carbonates. Samples then had their pH neutralized with multiple washes of DI water, then were put in dispersant. And right before they were analyzed with the laser diffraction analyzer, they went through sonication to just make sure everything was properly dispersed in the solution. So we analyzed the samples using a Malvern Mastersizer 3000 at Baylor University. And I used three main proxies during my analysis: the U ratio, the Twin Peaks ratio, and grain size index. Those are all ratios that compare the general abundance of larger grain sizes versus smaller grain sizes, but they include different ranges of larger and smaller grain size, so they can show slightly different things. As you can see over here, the U ratio, TP ratio, or Twin Peaks ratio, and the GSI for grain size index all remain pretty largely consistent throughout the stratigraphic column. You can see this slight cyclic pattern. It's easiest to see in the U ratio. I've pointed them out with some arrows. This can suggest repeated warming and cooling cycles. Lower U ratios can be caused by stronger patogenesis or weaker winds in a warmer climate. And the TP ratio and GSI follow a similar pattern to the U ratio, but it's a little bit harder to see. I then compared the U ratio and GSI together, and they are positively correlated, which is to be expected. They're both ratios of abundance of the sediment sizes. Though when you compare the U ratio and grain size index to the meteor diameter of the sediments, there isn't a really strong correlation, which is interesting. We think that it might be because since it's the ratio of like two peaks of grain size, the ratio will be the same, but as the abundance of one or the other shifts, or maybe the ratio is the same, but there's less overall, the median size will be skewed one way or the other. But overall, all three proxies suggest that the depositional environment remained largely consistent during deposition. There aren't anything that screams that there were any huge sudden shifts in the climate or environment in this area at the time of deposition. And I would like to acknowledge the Baylor University for the use of the grain size analyzer and the UTA EES Undergraduate Research Fund. I would also like to acknowledge Shankadeep Val and Dr. Majie Fan for mentoring me and helping me in this project. Thank you.